This iridescent disk is the most complex object ever built, holding the power of billions of transistors. But its origin is surprisingly humble. It begins here, in common sand, a raw material worth only pennies per ton on the market. Transforming this requires defying physics. 1,400 degrees, the pull begins. One tiny structural flaw here kills the entire production batch. One mistake here costs millions. This is a boule, a perfect silicon crystal weighing hundreds of pounds and worth a fortune. But now, we slice it thinner than hair. Engineering here is a war against friction. We slice the ingot into wafers 0.7 millimeters thin. What happens next defies expectations. This world is 10,000 times cleaner than an operating room. Here, the real industrial alchemy begins. The next stage changes everything. We polish the surface until it's atomically flat. Any microscopic bump would crash the laser later. One tiny uneven grain ruins everything. This machine uses extreme ultraviolet light to carve circuits. It's the most expensive tool ever built, but it operates in total darkness. A light-sensitive polymer is spun across the disk. It must be perfectly even to the nanometer. The slightest wobble costs millions. Lasers blast the circuit pattern onto the wafer. We are printing at the scale of individual atoms. Now the invisible becomes real. Hot plasma carves deep trenches into the silicon. It's a controlled chemical storm at molecular levels. 1 second too long, it's trash. We fire high-energy ions to change conductivity. This finally taps the true power of silicon. But the transformation is only halfway done. Our journey begins in rare quarries. We hunt for quartz veins with the lowest possible mineral impurities. But mining is the easy part. Massive crushers grind the stone into uniform pebbles. This increases the surface area for the chemical furnace. The heat required next is terrifying. We blast the ore with 2,000 degrees of heat. Carbon electrodes strip away the oxygen from the silica. This creates metallurgical-grade silicon. We turn the solid metal into a gas. By mixing silicon with acid, we create volatile trichlorosilane. Now the impurities have nowhere to hide. This tower acts as a massive filter. We separate pure silicon gas from heavy metals and boron. We are chasing 11/9 purity. The gas is pumped over hot rods. Silicon atoms settle out, growing into an ultra-pure solid form. This is the world's purest substance. These silver nuggets are worth their weight in gold. Even a fingerprint would ruin the entire batch. But they are still polycrystalline. To melt the silicon, we need a container that won't melt itself. This quartz crucible is single-use. One tiny crack leads to catastrophe. We flood the chamber with argon. This inert gas prevents oxygen from reacting with the liquid silver. Without it, the silicon would burn. Powerful magnets control the flow of the molten pool. We suppress the heat to keep it stable. The crystal begins to pull now. The neck must support the weight of a 200-kilo ingot. It's a miracle of atomic surface tension. If this snaps, the factory stops. We carefully increase the diameter. The ingot must be exactly 300 millimeters wide to fit the machines. But its internal structure is what matters. We crop the uneven ends of the ingot. Only the perfect center section is used for production. The waste alone is worth thousands. The ingot is ground to a perfect cylinder. It must be exactly 300 millimeters to fit the robots. A 1 millimeter error ruins the line. A laser carves a notch to mark the crystal's orientation. This tells the machines which way is up. Without this, the circuits won't align. We don't slice one by one. Thousands of wires cut the entire ingot into wafers at once. It's like slicing a diamond loaf. We lap the wafers between iron plates. This removes the saw marks and makes the surfaces parallel. Now we move into the microscopic. A bath of ultra-pure acid eats away the top layer of damaged silicon. It leaves behind perfection, but the acid is incredibly deadly. We round the sharp edges of the wafer. This prevents it from chipping or cracking during transport. Even a microscopic chip kills the wafer. This is the final polish. The surface is now smoother than any mirror found in nature. You can see the future in it. We grow a new, perfect layer of silicon on top. This is the canvas for the transistors. The real building process starts here. We bake the wafers in pure oxygen. This grows a glass-like layer of insulation on the surface. This layer is only atoms thick. We coat the wafer in light-sensitive chemicals. It must be perfectly even, down to a single molecule. Any dust here ends the mission. A quick bake solidifies the coating. Now the wafer is ready to receive the world's most complex pattern. The laser is about to fire. This plate holds the master blueprint. A single mistake on this mask will be repeated billions of times. It costs more than a supercar. These mirrors are the flattest surfaces on Earth. They guide light with accuracy down to a single atom. If one mirror shifts, it's over. The machine steps across the wafer, flashing the pattern onto every individual die with lightning speed. It's printing faster than the eye. A chemical bath washes away the exposed areas. The invisible circuit pattern finally becomes visible to the eye. But these lines are too thin. We use electrified gas to dig into the silicon. It carves vertical walls just a few atoms wide. The precision is almost impossible. We build vertical fins to control the flow of electricity. This is the 3D architecture of modern power. We are building a microscopic city. We grow a protective layer, one single atom at a time. This is the ultimate limit of manufacturing. It's like painting with atoms. This insulator prevents the chip from short-circuiting. It's the off switch for every bit of data. If electricity leaks, the chip dies. We drop the gates into place. These act as the valves that turn the transistors on and off. Billions of these fit on a fingernail. We blast the ends with impurities to create a path for electrons. The transistor is now almost alive. But it still has no connections. A split-second heat blast heals the crystal lattice. We are locking the atoms into their new positions. The heat is intense but brief. We fill the gaps with liquid glass to isolate every transistor. Each one must operate in total solitude. Now we need to wire them together. We coat the transistors in a new insulating layer. This acts as the floor for our wiring. Without this, the chip would short. We drill millions of vertical holes called vias. These are the tunnels that will connect our layers. Each hole is thinner than a virus. Before the copper, we add a barrier. This prevents metal atoms from leaking into the delicate silicon. One leak destroys the entire logic. We apply a thin seed layer of copper. This gives the electricity a surface to cling to. The gold color is purely functional. We use electricity to grow solid copper inside the trenches. This is the blood of the processor, but it's currently a solid mess. We grind away the excess copper. Only the perfect recessed wires remain in their designated channels. A single scratch here is fatal. We repeat this process up to 15 times. We are building a massive microscopic skyscraper of wiring. Total wire length reaches 30 miles. Every layer is sealed in protective glass. This ensures the wires never touch or interfere with electricity. The pressure inside is immense. We add the final skin. This tough layer protects the fragile circuits from moisture and physical damage. This is the chip's final armor. We add thousands of tiny solder balls. These are the feet that will connect to the motherboard. They are smaller than a pinhead. A computer scans for microscopic flaws. Even one broken wire means the entire die is dead. The rejection rate can be brutal. The wafer is complete. It now holds trillions of dollars in potential computing power and data. But it still needs to be cut. We touch the chip with needles thinner than hair. This is the first time the circuit wakes up. The first pulse is the deadliest. We blast the chip with data at billions of cycles per second. We are searching for hidden brain damage. Most chips fail this first test. Not all chips are equal. We sort them by speed. The perfect ones become top-tier supercomputer processors. The slow ones have a different fate. We use a laser to cut the wafer into individual dice. The precision is measured in microns. One slip and we slice a circuit. This robot moves faster than the human eye can track. It's handling millions of dollars every hour. But it must be incredibly gentle. We bond the chip to its permanent home. This green board acts as the chip's central nervous system. The connection must be permanent. We sew connections with thread made of 24-karat gold. It's the only way to ensure perfect signal flow. But gold is getting too slow. We seal the chip under a heavy copper lid. This prevents the processor from melting during heavy use. Without this, it burns in seconds. We cook the chips at high temperatures for hours. We are forcing any weak transistors to fail now. This is the trial by fire. We use X-rays to look inside the solid metal. We are hunting for microscopic cracks or air bubbles. The machine sees what humans can't. We use sound waves to find gaps in the glue. Even a tiny air pocket causes fatal overheating. Silence is the only good sign. The chip finally gets its name. It is now officially a product worth hundreds of dollars. But it hasn't earned its keep yet. Thousands of finished chips are packed for shipping. They are the most valuable cargo on the planet. A single pallet is worth millions. Human oversight is the final layer of quality. Behind every chip is 1,000 engineering decisions. The risk of failure never disappears. These chips are now ready to change the world. From this moment, they control our global economy. But the journey is far from over. The chip finally finds its purpose. It becomes the brain of a machine, processing trillions of operations. But it's just one of billions. In these digital cathedrals, our chips power the internet. They manage the world's collective knowledge in real time. The heat they generate is immense. These processors are now learning to think. They are the engines behind every AI breakthrough on Earth. They are evolving faster than us. This industry is the backbone of global power. A single disruption in the supply chain halts everything. Silicon is the new oil. On the road, these chips make life or death decisions in milliseconds. They see what the human eye misses. One software glitch is fatal. In finance, nanoseconds are worth billions. Our chips execute trades faster than the speed of human thought. The race for speed never ends. Some chips leave the planet. They are hardened to survive the brutal radiation of the cosmic void. They operate where no human can. Even in death, the chip is valuable. We harvest the gold and copper to begin the cycle again. But most silicon is lost forever. For decades, we double the power every 2 years, but we are finally hitting the limits of atoms. The wall is closer than we think. The next generation won't use sand. Quantum chips use the strange laws of subatomic particles to compute. This changes the definition of reality. This $500 billion industry rests on the shoulders of the world's most disciplined and precise human minds. A single burnout stops the line. Control of the chip is control of the future. Nations are spending trillions to secure their silicon sovereignty. This is the ultimate chess game. From education to medicine, this technology has become the invisible foundation of our modern human lives. We are now inseparable from silicon. It is a miracle of engineering. We took the most common material on Earth and gave it intelligence. But we aren't done yet. As we push toward the atomic limit, one question remains. What will we build when the sand runs out? The answer lies in the next revolution.